Hello everyone, today I have another video for you guys, and this will be, I think, one of my last videos in a big time. So I'll take a pause maybe for a couple of months. So this will be my last video, probably in the next month. I won't be releasing anything, but I brought you a good problem, and I hope you'll enjoy it and you'll find something new. So let's just dive into it. So this problem was in the Iberoamerican Olympiad 2019, problem 5. Here's the problem statement. So there's a Don Miguel, he places a token in one of the n+1 squared vertices that are determined by an by n board. And the move consists of moving the token from the vertex to another vertex, which is at most square root of 2 away, which means that you can move by side or diagonally by 1. And the path is a sequence of moves such that the token passes through each vertex of the n+1 squared lattice uh, exactly once. And we want to find the maximum number of diagonal moves that can be done in total. Okay, so and the way I looked at this problem, so we'll make a couple of key observations which will help us to drive this problem. Observation number 1. The only thing that we need to do is to find the amount of diagonal moves. So all the problem is revolving around is just diagonal moves. What does this mean? This means that it's the only topic that we need to investigate, diagonal moves. Okay, this brings us to a logical conclusion, which is chessboard coloring. Okay, what does that help? Well, the reason the chessboard coloring might be useful is because it keeps the color by a diagonal move and doesn't keep it otherwise. In such problems, it's always useful to have a tracking mechanism of what's going on. In this way, a chessboard coloring, even though it's quite simple and obvious, it works. So first of all, it hints us to two things. One, the problem might vary due to parity because the chessboard coloring responds differently to odd by odd boards and even by even boards. Number two, the only thing that we need to investigate is each monochromatic subcomponent separately. The reason why I say it is because these two components, they don't interact between themselves. And um, if two components, they don't react between themselves, they're independent. And if they're independent, the only thing that we care about is how can we split a component. What do I mean? Well, we need to split the board that we have into different paths. To illustrate, let's draw an example for n equals 3. So we have a 3 by 3 board, and we have these sequence of this lattice, basically. What happens? Well, when we have this lattice, what ends up happening is that we have these diagonal moves. However, if we look at this part of the graph and the rest, they don't interact between each other in diagonal moves. And because diagonal moves is the only thing we need to investigate, and all other moves can be assessed later, what we need to do, because we want to find the maximum amount of diagonal moves, and we have a fixed amount of moves in total, which is n squared plus 2n, we just need to find the minimal amount of moves along the edges of the board, which are non-diagonal. Why? And that's obvious, but what's the use of that? Well, this just means that we need to find the least amount of paths we can split this board into. And what I mean by paths is paths that are monochromatic. This means that they're paths that glide along the same color. So for example, here, this is a path. And we can split it into two. But we can't split it into one. And we are going to investigate that. And from this, we can drive the bound out because we can bound the minimal. So the way we think about it is like we want to split some sort of structure by moving into paths. This is a very common idea in graphs. So the whole problem will be revolving around a graph type structure. Well, and if it's revolving around a graph-like structure and you want to split it in like different paths, this hints that, well, uh, probably you'll be doing to do some, well, the bound will be not as harsh because this structure, for example, that I marked up in circles, we want to split in the least amount of paths. So it's just something probably to do with the degree of all the vertices. And here comes another idea. So the way math actually works, I think, for me personally, I'm a true believer that you can teach 10 people the same method, say induction or some trick or a configuration in geometry, and every person will perceive it differently. And I think that in martial arts, if you teach a person a jab or a throw, every throw, every jab, it's performed differently by every single person. So you can show the same technique to everyone, show the same technique, but everyone will look at this technique differently and see some tiny detail that they'll copy in their way. And what coaches do in martial art is when they see that, well, you have your own technique and you show it to kids and you need to show the basic steps, but every kid and every martial artist, he does this technique with a bit of uniqueness. The main core of what's going on is the same. And the reason I think everyone does it in their own way is because every person has a unique understanding of something, some subconscious understanding of what's actually going on. So if you show a throw in judo, then you can look at different details which you'll try to copy in your own way, and your body is used to it in your own way. I think this is applicable to maths. And the reason why it is applicable to maths is because I think on higher levels, the way you solve problems is you need to get exposed to a lot of other problems and hint at small details of your methods that you used before and look at small details that you can extrapolate onto bigger ideas. How's it related to this problem? Well, the whole thing about graphs, we have a n by n board. There's a common trick, and the trick is if you have a n by n board, so it's 3 by 3, and for example, you have some blue cells in this board. There's an interpretation from a board into a graph. The way that it works is you look at columns and you mark the columns as separate vertices on a bipartite graph. And the rows will be the other part of the bipartite graph. And if, for example, there's a blue cell in a certain row and in a certain column on the intersection of those two, we connect them with an edge. This is the way it works. Okay, and the follow-up is basically we rephrase the problem for a board so graph. If you look at straight up and you try to use the same idea, just thinking, okay, I use it here, I'll use it there. It won't work. The reason is because in this problem, the data structure is a bit different. The data structure is it differs a lot from the rectangle or a square. And here comes like this intuitive understanding. So the intuitive understanding is what is a square? Well, a square is like an array of different squares that we can move right or left or down or up. So we have four directions to go. Well, what is it to do? Well, the way the bipartite graph works is that basically you assign a coordinate to a bipartite graph, the coordinate of your movement. So if you move up or down or left or right, it's going to be represented by shift up or down in one part of the bipartite graph. And this small detail that you can pay attention to can help you to interpret this as a graph, but a different one. So you change the idea. And the way we change the idea is that we look at the diagonals. So the only thing that matters here is actually the diagonals. Everything the problem is about. And when I was thinking about this problem a couple of months ago, I knew that it was just diagonals. And this understanding that we have all our movement being tracked by diagonals, we don't actually need the columns and rows. We need this diagonal and this diagonal. So there are two types. And it's the same actual idea, but it's a bit different. So it's a bit tilted. And if we look now on the new picture, so if we say these are one diagonals right here. These are like the other diagonals. What will end up happening is we will have like this picture, which will be like, okay, we have three rows and four columns. Well, not necessarily rows and columns, but directed 45 degrees and 135 degrees diagonals. So three are these and four are these. Uh, what will end up happening? Well, if you just connect the vertices, then what we'll get is you'll have the middle one connected to everyone, and the other one's connected to the middle one. So we'll get a structure like this. But as we said, we just need to explore how many paths, the minimal amount of paths we need. The way the graph basically what a path is in the graph. Um, well, this is a very precise configuration to say something general about it. There's nothing really general or symmetrical. It's just symmetrical into two sides, not into all vertices. So you can't really make any general assumptions. So the only thing we're actually working is just the degree. It's the only thing we can really control. And the degrees of each vertex here, it's 2, 4, 2, and 1, 3, 3, 1. Okay. But each path that we know is 1, 2, 2, 2, 1. Now, what we think about is we have this chunk of line of edges, and we want to split it into paths. If we just go and take one path and we get rid of it, and then we take another path and we get rid of it, and we get another path and get rid of it until we're done, what happens at the end? At the end, we will have that all the degrees will be 0. Okay, but 1, 2, 2, 2, 2, 2, 1. Every single vertex, except for two of them, won't change the parity. And exactly two will change the parity uh, of the degree. How's that useful? Well, zeros are all even, and we have 4 degrees on the right-hand side that are of an odd power. This means that we need at least two paths. So this is already a bound because we need at least two paths to make all those even. Because if we have one path, then the parity will remain as odd, and you can't get that. Okay, so this is like a similar idea. So the way you come up with this idea is just again you look at the Euler cycle proof or the anything like that, you will immediately see this. So this is the same story under a different angle. Right? And okay, and the way you look at this in general is that in general case what will end up happening is you'll have 2n minus 1 vertices here and 2n vertices here. And power of these will be 1 or 2, 4, so on, 2n, 2n minus 2, blah, 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 4 and 2. And here it will be 1, 3, blah, 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 2n, this 2n minus 1 vertices, right? Or no, yeah, this 2n minus 1 vertices. And then you have here 10 minus 1, and then you have 2n minus 2, 2n minus 1 again, and then blah, 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 3 and 1. And so uh, you'll basically have 2n odd vertices, which will end up giving you n different paths on each subcomponent, right? So this means that you'll have at least n different paths. And this is for the black cells. Same will happen with, well, no, the like the black color. We color the chessboard black and white. The same will happen with the white color. So we'll end up with having like, if we just delete all these lines along the edge in any path, and we look at the colors, so we'll go. So the colors will obviously go black, black path, white path, black, white, white, black path, white path, path, white path, and so on, so on, so on. And each of black path and white path, there'll be n. We have, and this is in the case that we have, well, n plus 1 being divisible by 2. So if n plus 1 is divisible by 2, which means that n is not divisible by 2. In this case, what will end up happening is that we, in our situation, we have n plus 1 squared vertices, which means that we have n plus 1 squared minus 1 edges, because in our path. And we know that we have basically n black subcomponents and white subcomponents, and they go one by one in order. This means that we'll have uh, n edges, at least in between them. So this means that this is a bound for this. And I think a lot of people have this like very, very strict idea that you have to do the example first and then the bound. I think that's completely wrong. I think you should try both. I think that a lot of people think that example might help you to understand something about the bound. Well, what people don't realize, it works vice versa. Something about the bound can help you to understand something about the example. This was illustrated when I was solving EGMO P6. Same idea. I showed the bound and then I got something in the example. But okay, so now what we want to do is we just look at the other case. And the other case is when we have n plus 1 being odd. In this case, it's a bit different. So the reason why it's different because you'll have one structure being this, uh, something like this, and the other structure of the graph subcomponent will be something like this. So these two are different. Um, but we'll just look at this because this path, actually, the secret is it can be passed as one thing. It won't give us any information. However, this one is the one we're interested in. And if we look again at the same idea with tracking the movement, we again go into this idea of looking at this bipartite graph. And the way it will work in this case, it will have an odd amount on both sides, precisely n plus 1 on each side, the side length here, n plus 1 here. So this is the case where n is even. And the way it goes is you say, okay, we have one here. So the center ones are connected with everyone. Then the farther you go from the center, the less they're connected with. So the ones right near to the center, the only ones they're not connected with are the ones at the edge, and so on, so on, so on. So this is the one you get for n equals 5. But the main pattern you need to spot is that it just goes by the degree. So it goes 1, 5, 3, 1, 5, 3, 1, 3, 5, 3, 1. In general case, 1, 3, 5, blah, blah, 2n plus 1, 2n minus 1, 2n minus 3, blah, blah, 1. So it's just all numbers up and then down. Then we have 1, 3, 5, 3, 1. In this case, note that we have 2n plus 2 vertices that have odd degree. At the end, we want all of them to be even degrees. This means that we need at least n plus 1 paths. So this is not n plus 1 divided by 2 that we had in the previous case. This is n plus 1. And the other thing to mention is that, well, you basically, in this case, by the way, we have 2n. That's my bad. It's just n squared. Because we have ny blocks, so we have a black, and white, and black, and white. And of course, we need like all these ones here. So this will give you at least 2n. Yeah, that was stupid. Because yeah, whatever. This is just n squared because n, y, and black they both need connections. But in this case, we need n plus 1 black ones. And the black ones can't be between each other, so there can be a block of black ones. and right after that, a block of black ones. So there should be at least one block of white ones in between. So if there are n plus one black blocks, uh, then what's basically happening is that uh, well, uh, we want in ideal world we would want something like black then skip again black then skip then again black, but every single block after black there's n plus one of them. So and now this gives us a bound on n squared plus n. Uh, yeah, because we need at least n plus one different black blocks, and uh, for every oh, wait, did I get somewhere? Um, okay, so for n equals even, so for n say equals 2, the answer so for if n is equal to 2, yeah. So this for n equals odd, I was right. It's n squared plus n. I was right, my bad. The reason it's n squared plus n is because uh, it's just because we have um, oh yeah, of course, of course, of course, of course. Because we were assuming that this is 2n of them. Yeah, yeah, I made a mistake here. I'm sorry to confuse anyone. So if there's 2n of them here, then we need n pairs. So in this case, when we have n plus 1 squared vertices, we need like minus 1 because total edges, and then we need n divided by 2 and n divided by 2. The reason is we need n divided by 2 of black ones. If there are 2n total here uh, of edges. Okay, so and in this case, we have n plus 1 black ones, and there needs to be someone in between them. So it just can be black, 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 black. It should be black, then white, then black, then white. So we need a total of at least 2n plus 1. And this gives us a bound in the square. Now let's show the examples. So let's start off with the case of n being odd. So if n is odd, we know that the answer is n squared plus n. And the reason is that basically we have, if we have like this structure here, we want to split it into n divided by 2 stuff, different paths. And it's quite simple to do so. It's just like this and like this. So in general case, if we look at general case, so it'll look something like this. Here, then here, and finally here. That's for one color, and for the other color, it'll go similarly. It'll go like this, and like this. And this is the optimal. We showed that it's the optimal. And you see now we showed using the bound that we had, we can limit what cases should we look at. And by easing up what the work is, we can easily find the example. So, and then just by filling out the missing parts and missing parts going. Yeah. So this is the example for n is divisible by not divisible by 2. And the answer is n squared plus n. And the example for the even case is a bit trickier. So here we need to split all these vertices here. We need to split it into n groups. But again, if you just analyze what we had, we don't really care about the white vertices, well, not the crossed ones. We just care about the configuration of the black ones because the white ones act as fillers in between, and the black ones we need to just split them into um, five groups in this case, and that's again quite easy. It's just this line, then this line, then this line, and that line. So you get something like this, 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 and these are separate. And then in order to just fill out the other spaces, it's quite easy to do something like, well, we'll need two n of them. We showed that we need 10, well, basically, we need n plus one of these ones, or yeah, we just need n plus one of these ones, and n of these ones, and n of these ones will just go like this. This is quite easy as well. And then we just need the filler ones, and the filler ones are just this, 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 and this, and we're done. Yeah, and this is two examples, and we're done. I think that this was a very instructive video about how to extrapolate different ideas, and I think that like I hope that it was a bit useful to find this new idea and how just in general you approach different stuff. And I just found this idea nice about using diagonals as your bipartite graph. And yeah, I wanted to thank everyone for watching. Have a blessed day, and thank you for joining in. Goodbye.